Hello students. Today in this particular lecture, that is about the testing techniques in the software engineering, we'll be considering or we'll be discussing two important testing methodologies which are actually the types of the specification that we discussed earlier. That's black box testing. So these two testing techniques are or testing methodologies are actually the boundary value testing and the equivalence class testing. Okay, so we'll be discussing first the boundary value testing, and then we'll go on to discuss the equivalence class testing. So boundary value analysis is basically a method of or a type of the black box testing or specification or function based testing. Okay, so it basically tests the elements which are towards the extremities of the input domain. Okay, so we know that there is always a more chance of having error when the elements are at the extremities or at the boundary of the partitions, input partitions. Okay, so when we test this, actually we can consider those boundaries to be the values which will generate the test cases for testing the inputs. Now, maybe due to a budget constraint or time constraint, we may not be able to do exhaustive testing of the input. In that case, we can basically take the large pool of inputs to partition into some sets from where we can take the boundaries to generate the test cases. Okay, so there are two techniques here basically used for this kind of test case generation are the equivalence partition and the boundary value analysis. So as I have already just told you that it is the elements which lies in the extremities or the boundaries of the partitions that are considered. The input values which lies in the extremities are considered to generate the test cases. Okay, so these extremes are like something like, you know, where start, end, maximum, minimum, okay, or just inside the maximum or just list one value than the maximum, or just above the minimum are the boundary values which are actually taken for this kind of test case generation. So this is as you can see, the boundaries, the minimum, just above the minimum, and a nominal value in between in the valid range is taken as also to generate the test case, and then again the just below the maximum and the maximum. So there are basically 5 considerations which are values which are taken to generate. So this is what has been shown with the input domain here. The same example with a diagram here, that is for a input value x, input variable x, we consider the extremities where this is the maximum, one less than maximum, the nominal values, the minimum, and one above the minimum. So we can consider one example here. Suppose there is an exam which has been conducted, okay, and the pass mark is 50%, and merit is at the 75%, and the distinction is supposed at the 85%. Okay, so the extreme values or the boundaries in this scenario is something like this. To pass, it may be 49 or 50 or 51. Okay, and for merit 74, 75, 76. For distinction 84, 85, 86. Okay, so boundary value basically validates not only the valid input values, also the invalid input values in the boundaries, in the extremities. take another example here. Suppose we have an application where we are inputs as the age, which the correct range or the valid range we have determined that field is 18 to 56. Okay. So with the boundary value analysis, we know that the valid range is are the boundaries which are the minimum which we have taken as the valid range as the 18, just above minimum is 19, then maximum is 56, just below 56 is 55. So these are the boundary values. And invalid is the 17, which is the just below the minimum, and one above the maximum, 57, is the invalid. So when we generate test cases, we'll consider this kind of test generations. That is, the minimum boundary value is the 18, maximum boundary is 56. So valid inputs we have taken already. I have shown in the previous diagram. What is the invalid values we have taken? And the boundary, that's also I have written. So test case will be the enter the value 17, which is just below the minimum. So it is invalid. 8 minus 1 is 17, because 18 is the minimum. So enter the value 18, which is the boundary value. So it is a valid input. Test case 3, 1 above the minimum, that is 18 plus 1, the 19, valid. So similarly, for the maximum, the boundary is 56. 1 below the maximum, 56 minus 1, 55, is the boundary value which is valid. And 1 above that particular boundary value is 56 plus 1, 57, is invalid. Okay. So these are the test cases that can be generated by considering these particular boundary values for this particular field or particular variable. Similarly, take another example where we are accepting a name and we are determining the size of the string that can be accepted as name. Okay. So to check this error condition here, that is to test the condition here, that is the minimum is, suppose the length which is accepted is 6 to 12. Okay. So minimum is 6, maximum is 12. Like in the previous case, we have 6 in the boundary, 7 just above the boundary. Okay. 11 and 12 are the other extreme. 12 is the maximum, 1 less than the maximum. Invalid range is in the boundary value analysis is 5, 1 less than the maximum plus 1. That is 12 plus 1, 13 is the invalid. So the test case generation will be something like this. We'll have the maximum boundary value, that minimum boundary value 6, maximum boundary value 12, that we have already discussed. So test case 1 is the 5, the length of, that is the text length of 5, that is invalid, 1 less than the minimum. Then comes the text length of exactly 6, that is the boundary, the minimum. So similarly, we have the text length of 11, that is 1 less than the maximum, which is the valid range. Okay. Text length of 12, which is the boundary, is the valid, and 1 more than the maximum, which is 13, and which is invalid. So this should be the output of the test cases given the inputs. Can be actually, boundary value analysis can be done in a uniform manner. That is, the basic form of implementation is to maintain that one variable at the nominal in between, that is in the valid range. It can be anywhere in between the valid range, somewhere, maybe a normal value, or we can consider an average value as well. So, and allowing the remaining variables to take the extreme values in the valid range. Okay. So in the normal boundary value, what we consider, we don't consider the invalid parts here. We consider only in the valid range. What are those valid range? That is the minimum, 1 more than minimum in the extreme boundary of the minimum value. Then comes the nominal. It may be average in between the minimum and the maximum somewhere, and then the maximum value and one less than maximum value. So on entire these 5 set of values are in the valid range, which we consider as the normal boundary value testing. So graphically you can show this here. That is the foul range here is see, this is the minimum one more than the minimum in a valid range. Similarly, one more than the minimum in the valid range. The normal, one less than the maximum, one less than maximum in the valid range. This shows the valid range of the values, which we call as the normal boundary value testing. This is like boundary value testing, but with the exception that we consider here the invalid entries. Okay. So when we try to consider the legitimate boundaries, we consider that as well. That is the invalid entries. Okay. So in the robustness testing, we consider minimum plus in the valid range as well as minimum minus, which is the invalid range. Similarly, nominal value we take, maximum we take in the boundary, one less than maximum in the valid range, and one more than maximum in the invalid range. So here you can see in the graphical form the robustness testing. That is, we can have minimum, one more than minimum in the valid range, one less than minimum in the invalid range. One less than minimum in the invalid range, one more than minimum is the valid range. Similarly, for the maximum values, the other extreme, one less than maximum in the valid range, one more than maximum in the invalid range. One less than maximum in the valid range, one more than maximum in the invalid range. Okay. So both these cases, both these sides are taken into consideration while generating the test cases. Worst case boundary value testing is another methodology. In the boundary value testing itself, these are actually variations of the boundary value testing. Okay. But here, actually, we make use, in the earlier cases that we have discussed till now, actually we have taken a boundary value with respect to a single foul assumption. Okay. That is, we consider the fouls to be arising in the single values. So while if we consider more than one values that can have the extreme value, okay, then we have to go for the worst case boundary value testing. Okay. So in case of the electronic circuit analysis, this kind of worst case analysis, it is called as the worst case analysis, and we take the same concept from the electronic circuit analysis to here in case of the software engineering test case generation. Is that we take the Cartesian product of those values which are taken by the variables. Okay. So what is the Cartesian product of the values? That is, we have two sets, then for every value of set there is every combination of the values from the second set is considered and is taken. Okay. So the combinations of different values are taken in the all possible cases among the two cases, among the two sets. Okay. That is the Cartesian product. So it is we take the Cartesian product of the two sets to generate the test cases. So take an example here. The two variables, say x1, which the extreme ranges are from, for the x1 variable, suppose is from the 10 to 90. The range of the values taken by the x2 in the valid range can be from 20 to 70. Okay. So by going through the normal boundary value analysis, we know that for x1 the boundary is 10. Okay. So in the valid range, 1 above 10 is 11, which is in the valid range. There can be a nominal value anywhere in between. Say we are considering it to be 50. Then there is the maximum boundary value is the 90. One less than the maximum is the 89, which is the boundary value. Okay. So which is considered as the is in the boundary value for test case generation. So similarly, so this becomes one set of the boundary value taken by the variable x. Another set, which is the range of x2. Accordingly, in the valid range will be 20, 21, 45, 69, 70. Now, we take the Cartesian product. That is, for every value of x1, for 10, we first map to 20, 10 to 21, 10 to 45, 10 to 69, 10 to 70, okay, to generate the test cases. Similarly, then we go on to map 11 to every values to generate the test cases. 11 to 20, 11 to 21, 11 to 45, 11 to 69, 11 to 70, okay. That way, we go on mapping the values in the input domain in the boundary value analysis to generate the test cases for this particular testing. So it is this procedure is called as the boundary value testing. So this is what we achieve in a graph when we do such kind of Cartesian product between the two sets to generate the test cases. Okay. So we have 5 values here. As you can see there, we had the 5 values in that example. So we have 5 into 5, 25 different test cases generated. So 5 into 5, you can see this is 5, 10, 20, 25. So there are 25 test cases that are generated in the worst case boundary value testing. This is what exactly has been described here in this slide. That is, the test cases is 5 into 5, 25. Okay, that is the number of testing points. So these testing points are basically the minimum, minimum plus, nominal, maximum minus maximum. So combination of both these values are taken from the range of x1 and x2. Now this is the entire combination after taking the Cartesian product. In that example that we have discussed about x1 and x2, I have explained that 10 maps to 20 for the first test case, for the second test case 10 to 21, for the third case 10 to 45, for the fourth test case 10 to 69, for the fifth test case 10 to 70. So then again it goes to the second value of the first set, 11 to 20, that is the first value of the second set, 1120, then 1121, 1145, 1169, 1170, then goes to the third value, that is the nominal value of the first test case, first set. So that 50 to the first value of the second set, 20, 50, 20, 50, 21, 50, 45, all these are different test cases which are generated by taking all the combinations of the two sets. That is the Cartesian product of the two sets. So apart from these variations that we have discussed till now, up to worst case, there will be this another variation which is called as the special value testing. So special value testing is basically based on intuition. It is based on the intuition of the tester to generate the test case. From the experience of the user, of the tester, of the input set, okay, and also the domain knowledge of the input set, the tester basically generates some specific test cases to generate the test cases. So they can also identify some soft spots within the input range to take the test cases, okay, to generate the test cases. So there is actually no guideline for this particular special value testing methodology. We can say the guideline can be only user-based engineering judgment, okay, because this is all based on the intuitions. So it is as already whatever you can understand from my description, that is the special value testing is basically based or dependent on the ability of the tester, okay, that is the capability of the tester, because it depends on the experience of the tester, the domain knowledge of the tester, okay, that is the knowledge of the tester about the input domain of that particular application, okay. So the tester knows where the soft spots are, where the error may occur. So accordingly identify the places to the input values to generate the test cases. So this is called as the input value testing. Similarly, there is another methodology or variations of the boundary analysis, which is called as the random testing. Random testing is also a form of functional black box testing when there is less time in the tester's hands to write the formal test cases. Okay, so what they do, instead of identifying that minimum, minimum plus, nominal, maximum minus maximum, they use some methodologies to generate some random numbers. Okay, so they basically use the random number generator to pick the values from the input domain to generate the test cases. Okay, so what happens is that advantage of this particular methodology is that it basically avoids any form of bias in the testing. Okay, so because it is the value is taken from the input domain but through a random number generator, so there is a less likely to be any bias in the testing methodology. So that is another variations of the boundary value analysis. So equivalence classes is another methodology for actually doing the functional testing or specification based testing. Okay, so important aspects of these equivalence classes is that they form partitions of the sets. Okay, so what these partitions indicates is that the partitions refers to the collection of mutually disjoint subsets whose union is the entire set. So we have a particular set, suppose S, we have some values as the input domain for the testing, and we take the partition in a such a way that some values which are, say, the first 5 value, then the next 5 value, then the next 5 value, but they are basically disjoint to one another, and union makes the entire set. Union of those subsets make the entire set, but they are mutually exclusive, or they are disjoint. So they are disjoint subsets. So since it is based on the mathematical concepts of the equivalent relation, since these subsets are determined by the equivalence relations, so the subset has something in common based on which they are partitions. Okay, so idea of this particular equivalence testing is that we identify test cases by using elements from, or say one element from each equivalent class. So what happens is that instead of, since they have some commonalities in the within the subset, so if we take only one, pick up one particular test input from that particular equivalence class, then it represents the entire subset. Okay, so that way we can identify one element from each of the subsets and we can generate the test cases. So if the equivalent classes are actually chosen, they are from some common subsets which have some commonality in between the elements there. So when we pick up one element from there, it represents the entire subset. So, and then again another value we pick up from the another subset. So definitely the redundancy will not be there. Okay, it basically reduces redundancy. Take one example here. Suppose we are generating the test cases for the triangle problem. Now we are trying to cases for the equilateral problem to determine that particular triangle is a equilateral triangle. So this is here, the equivalence relation is basically from those which are the equilaterals. Okay, so if we identify or pick a triple 5, 5, 5, then probably we are not going to get much information by taking again 6, 6, 6 or 100, 100, 100. Okay, because the 5, 5, 5 is a good enough representation of that representative of that particular equivalence class. Okay, so it is, we don't have to again test for 6 or 100, 100, 100. So key, or we can say, or the craft of the equivalence class testing is the choice of the equivalence relation that determines those classes, those subsets. Okay, so suppose if our function has 3 variables, A, B and C, and the input domain consists of A, capital B, capital C. Okay, Now suppose we choose an appropriate equivalent relation which induces suppose the following partitions. Okay, so our input domain is A, B, and C. We are trying to take the input variables, the three variables A, B, C, small a, small b, small c, from those input domains, capital A, capital B, capital C. And we have an equivalent relation which partitions these three sets into some equivalence relation. First domain is first set is partition into A1, A2, A3 with that equivalence relation. Similarly, for the B domain or the B set is partition into suppose 4 subsets. Okay, B1, B2, B3, and B4. And then again C is partition into 2 subsets, C1 and C2. Okay. Now then we can actually pick up an element some A1 from the partition A1. Okay, because those are A2 and A3 are the equivalent relation, so A1 is sufficient to represent A1. Similarly, from the B input domain we can have B3, and from the C input B3, suppose from the B3 partition in the set B3 partition. Similarly, C2 can be from the C2 partition. Okay, so these are the valid inputs we can select from some subsets from this particular subsets which have been created. Now there are some variations of this equivalence relation. Suppose first we will discuss about the weak normal equivalence class testing. What is called a weak normal equivalence class testing? Okay. So weak normal equivalence class testing is that it is accomplished by using one variable from each equivalence class in the test case. Okay. So we pick up only one variable, like say A1 belongs to A1 subset. So that is one variable. Okay. So from each equivalence class to generate the test case, we take exactly one value. Okay, one input value. So in the previous case, we know that the B domain has 4 subsets. So we have the one values. See, the largest subset created is from the B value, B set, because you can see here that is B has 4 partitions being created: B1, B2, B3, B4. These are the 4 subsets. Okay. So taking one value from each of these B subsets, we get, see, B1, B2, B3, B4. B1 represents the capital B1 subset. B2, small b2 represents the capital B2 subset. Small b3 represents the capital B3 subset, that way. Okay. Now, to generate the test cases, first we take the one value from the largest partitions, that is the domain which has got the largest partition. So B1, B2, B3, B4. After that, we consider the other partitions of the other input values, other sets, that is the other domain. The set A, which has been partitioned into 3 subsets, A1, A2, A3, with the same equivalence relation. So here we have 3 partitions, so it goes serially A1, A2, A3, and since it is one less than the maximum value partitions, so the initial value is again repeated. So we get A1 again here in the last test case here. That is, these are the test case numbers. Weak equivalence relation 1, weak equivalence relation 2, weak equivalence, that is the WE3 and WE4, weak equivalence. So here, again, since the C partition, that is the C domain, is divided into 2 subsets, right? C1 and C2. So C1, C2, and again C1 gets repeated and then C2 gets repeated. So we have the repetition of the 2 values here because that is the least number of partitions that is being created. Okay, subsets being created. So this is what the weak equivalence relation testing methodology is. That is weak normal equivalence testing. So diagrammatically, we can take one example here and show this weak equivalent relation testing here. That is, assuming that there are two input domains, x and y. Okay, the partition of the input x, that is the first subset, is suppose the first set is x. X is partitioned into 1 to 10, that is one subset. Then 11 to 20, the second subset, and the third subset is 21 to 30. So we get three partitions. Which are those equivalent partitions? This is the x range. This is the first partition, second partition, third partition. So we get three partitions in the x domain, the x values. Similarly, we have another variable which is given by the y. Y has 1 to 5, 6 to 10, okay, with the equivalence relation. Then 11 to 15 and 16 to 20. So we have 1 to 5, 6 to 10, 11 to 15, 16 to 20. Okay, so we have four equivalence partitions being created here for the y range. Okay, so equivalence classes are, number of equivalence classes are 4. So one value from each of the equivalence relations gets selected. So it is, we get three values being selected from these values from the equivalence relation in the x domain. Similarly, four values from the equivalence relation in the y domain. So it is, say, this is the correct range is, suppose you can say somewhere in the 224, one input value, one particular value which got selected from the suppose in the valid range 2 to 24. Okay. Similarly, we may have an xy value being get selected, that is one. See, this is one equivalence relation, that value 2, and in the input range this is the 24 is the valid range. Similarly, 8, 15, 8 somewhere here in the correct valid range, and 15 is somewhere here in the valid range. So this one gets selected. Similarly, you can have 13 in the valid range, 4 here, so 13, 4 on the valid range. Again, there 17 is in the valid range, 17 in the, because it's less than 20, and 23. So we get another valid inputs equivalence relation here. Another variation of having the test case generated for the equivalence classes is the strong normal equivalence class testing. Okay, so strong normal equivalence class testing is based on again the way we discussed in case of the boundary analysis, boundary value testing. It is based on Cartesian product of the partition subsets. Okay, so if we have a partition, for the set A, set B, and set C, and we have 3, 4, and 2. Suppose there are partitions from A, is 3 partitions being created from A, and 4 partitions created from B, and 2 partitions created from C. Then total number of test cases generated will be the 24. That is 3 into 4 into 2, because this is the Cartesian product. Okay. So taking the same example that we discussed earlier, that is the B subset being created into 4 values, that is the B1, B2, B3, B4. A subset being created in 3 values, 3 partitions, A1, A2, A3, and C have the 2 values, C1 and C2. We can have all the possible combinations. This SC means this is the, see, whenever you are generating the test cases, you must have a test case number, which has to be, every test case has to be identified by a test case identifier. So it is SU1 is the first test case, okay, which will have the value A1 from the partition A, so B1 from the partition B, and C1 from the partition C. Okay, so for every value of A1 you have the B1, 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 and for every B1 we have the C1 and C2. So that way you take all the combinations, and you can see the Cartesian product gives you all these combinations. For A1 you have the entire iterations, and for B1, B2, B12, B22, B3, there are 2 values for B32. Similarly, because we have only two values for C, two partitions for C. So for every every combination of A1 and B, we have a C combination. So we have all these different combinations. Okay. So after completing the A, for every value of A, we go for A2. Again for A2, we have take the first B1 value and the C1 value. Again for B1, you take C2. Then you increment the B1 by the other value, take the B2 value, and the corresponding will be the C1 for B2, C1. That way, you have the entire range, the Cartesian product values that you consider for testing. So in total, you have 24 test cases which are generated for the strong equivalence test. So what is the advantage of having such equivalent class testing method, strong equivalent class, is that it guarantees that we have a notion of completion in two senses. Okay, that is, we cover all the equivalence classes, are covered, and we have one of each possible combination of inputs. So since we are considering the Cartesian product, obviously we have all the possible combination of inputs. So basically, this test becomes a complete test. So with diagrammatically, it can be identified this way. That is, take one example here with the same example that we discussed earlier. In case of the weak, here you see the equivalence classes for the X domain is 3. This is valid range, this is valid range, this is valid range. For the Y domains are 4. This one, this one, this one, this one, right? And we take all the possible combinations. That's why you find a dot in every square here. Every intersection point you have a dot. So obviously you have all the possible combinations being got tested. Okay. So there are 3 into 4 because 3 for one variable, that is the one set, 3 partitions. Another set 4 partitions. So 3 into 4, there are 12 cross products that you get, Cartesian product that you get. So we have 12 different values which gets tested. Okay. Weak, robust, in the invalid part. That is the invalid inputs to be considered. Okay. So weak robust is similar to the weak normal, in the sense that we only also consider the equivalence class which is not in the valid range. Okay. So sometimes this considering the invalid or identifying what should be the invalid value becomes little difficult. Okay, but this is actually required, and it is for good testing methodology. So here you can see, taking the same example, this is what we discussed earlier in case of the normal equivalence class or weak equivalence testing. So now we have 2 other equivalence classes which are in the invalid ranges. So here for the X values, we have 1 below, 1 above, that is the invalid ranges. Similarly for the Y ranges, 1 below this side and another on that side in the invalid ranges. So this is in the invalid range. The pink color dot you can see, that is in the invalid range. So these 2 values also needs to be tested. So this becomes robust equivalence testing. Okay. So in the case of Y partitions, now instead of having 4 partitions which were in the valid range, which is when we discussed in the weak equivalence testing, we know that there are 4 partitions in the valid range in the Y range. Now we have 6 partitions, right? 2 invalid partitions. Similarly for the X range, we had 3 partitions in the valid range. Now we have 5 partitions which are in the invalid range. Okay, 2 in the invalid range. Similarly, we have a strong, robust equivalence class testing. So strong robust is like strong normal, except that the all the invalid inputs are now considered. Okay. In the same way, we take the Cartesian product and we also consider the invalid inputs in that Cartesian product. So when we have the invalid partitions considered, we have something of this sort. That is, we have two partitions each range in the invalid part. So we have earlier we had three partitions for the X range, X set in the valid range. Now we consider two invalid values, invalid partitions. So we have total of 5. So similarly for the Y range, there were 4 valid partitions, 2 extra now. That is the invalid range. So we get total 5 into 6, 30 test cases for generating the test cases. So there will be that is the Cartesian product of the equivalence classes. That includes the invalid inputs. Thank you. So this is all about the boundary value testing as well as the equivalence class testing. And remember, these two testing methodologies are widely used testing techniques to generate the test cases for the functional or specification based testing. That is this is the part of functional and specification based testing, where we take those inputs domains to generate the test cases using either of these two techniques. Okay. Thank you.